So welcome everybody to this online talk organized by the ENLIGHT Rights Alliance in conjunction with the Arqus University Alliance. I'm happy to be here moderating this session, and I have the immense pleasure to announce the talk by Professor Nepomuceno. Well, Dr. Heriberto Nepomuceno is an associate professor at the Center for Ocean Energy Research and the Department of Electronic Engineering at Maynooth University. He has been a visiting research fellow in different universities, such as the Technological Institute of Aeronautics in Brazil or the Imperial College in London, among others. Heriberto is too a senior member of the IEEE and elected chair-elect of the IEEE Technical Committee on Nonlinear Circuits and Systems. He's also the Deputy Coordinator of the Technical Committee on System Identification and Data Science for the Brazilian Association of Automatic Control, but also he has served as Deputy Editor in Charge in other journals, like several of the IEEE journals, and serves as an associate editor of many other journals. He has published more than 90 journal papers, more than 200 conference papers and book chapters and editorials. And his research interests include computer arithmetic, chaotic cryptography, green computing, ocean energy, sustainable circuits and systems, and system identification. But also he's very interested in the open science topic. He's also a member of the Arqus Open Science Ambassador Network. And okay, that's all. Thank you very much, Professor Nepomuceno, for this wonderful talk that we are going to receive today. And feel free to start when you're ready.
Okay, thank you very much, Pablo. Are you listening me very
Yes,
nice? Okay,
exactly.
fantastic.
Perfect.
Thank you very much for this opportunity, for the organizer to give me time to think. And I will start for the title of this presentation. I call it The Relevance of Non-Reproducible Research. I think that irrelevance has been chosen to be provocative. Of course, to say something that is completely irrelevant, it's also very strong statement, but I prefer to say that more than because I think that everything that we do in life has some meaning. But here the relevance, because there is a contradiction that I'd like to explain between the very fact what we call as science and the capacity to be reproducible. So if it's not reproducible, hopefully at the end of this talk, we will be able to discuss a bit more about that. But my core attention is that there is an intrinsic relationship between science and reproducibility. So this is the main message that I'd like to explore in the next couple of slides. So first of all, what science? So scientific theories are distinguished from myths merely in being criticizable and in being open to modifications in the light of criticism. So I do love this guy, Karl Popper. Probably most of you have the opportunity to read something about this guy. And for me, it's really important because sometimes we think that when you publish a paper, that the game is over. And it's not the fact. It's not the moment that the game is over. In fact, when you publish a paper, the game is just started. So when you publish our results, it's the beginning of a long journey to accept the criticism. It's not the final answer, as many people believe. So as you have a published paper, we have just published a dogma that cannot be criticized. That's not science. In fact, when you publish a paper, we open our windows, our doors to be criticized. But that's the point. So how could it be criticized again and again if other people cannot reproduce our results? So there's no way about that. And look at that. If I was quite strong in my title, can you imagine how Karl Popper when they compare scientific theories are distinguished from myths merely in being criticizable. So that's the point. A myth cannot be criticized. A dogma cannot be criticized. But as science we could be. So if you don't think that, there's another quote by Karl Popper that he used to say that science is everything that could be refutable. So if you think that when you publish a paper, it cannot be changed, that's not science, because someone can find, or even yourself can find a mistake, can find something that could be improved in your thoughts, in your theory. So that's the beauty of science. We never stop to become more and more close to the truth. So, but what's science? All of science, the whole edifice, is a working draft, subject to revision and reconsideration. So this is really important. If you don't think that we are going to change, we are not going to be able to be a scientist. But sometimes when you are looking for a specific definition, it's not so easy. So when I'm looking for this again and again, and probably I come up with many definitions and concepts of science, but this is one of science of definition that I thought that it's quite useful. Science is a mode of inquiry that aims to pose questions about the world, arrive at the answers, and assess the degree of certainty through a communal effort designed to ensure that they are well grounded. So this is the mode. So when you are going to try to assess in certain degree about something, and there's another word that I'd like to express, this is really quite interesting. This is the word communal. So communal, that is a collective effort. So it's really important to see a published paper as a connection with a scientific community. This problem in reproducibility is not new. Probably all over the past centuries, at some point, this has been a topic of interest. But very recently, The Economist has published in Sakova How Science Goes Wrong. So in this issue, they ask about a simple idea underpins science, trust, but verify. So it's really beautiful, this very simple statement. You should trust science, but you should verify. And usually many companies, they use science as a way to present the trust. And you could see probably many pharmaceutical companies that say that my medicine or my drug has been scientific tested. And it means that they found the truth. That's not. You should verify. And probably many drugs have presented some problems. So results should always be subject to challenge from experiment. So this is another point that I'd like to emphasize. Although we should trust science, we should challenge with experiment. So a crisis. So in this topic, they say that more than 70% of researchers have tried and failed to reproduce another scientific experiment, and more than half have failed to reproduce their own experiments. Those are some of the telling figures that emerge from Nature Saver of more than 1,500 researchers. And for me, it happened to me, particularly in my own research, reproduce their own experiments. And that's why I try to, I went to open science, because I thought that I was not able, when I found some of my computer simulation, that I was not able to reproduce, I thought that's so ridiculous to myself. I thought so small. I thought so naive. How could it be it? But the problem is that any of us, if we are going to try to simulate, to reproduce a computer simulation with more than 5 or 10 years old, we are going to face many difficulties because all code probably have been not updated. And to update a code, it's almost sometimes to produce a new code. So this is a problem that make me think about upside. So how could guarantee reproducibility in my own science? It's important to try to say something about reproducibility versus replicability. Sometimes these terms are used with no distinction between them. So we can say reproducibility, it's the same as replicability. But sometimes there are some differentiation. Reproducibility refers to instances which the original research and data and computer's code are used to regenerate the results, while replicability refers to instances in which a researcher collects new data to arrive at the same scientific finds as a previous study. So those words, sometimes they refer in the literature, is slightly different from each other. And to be honest, I don't use replicability quite so often. I use reproducibility as a broad meaning to refer in both aspects of reproducibility and replicability. But the core idea here is that you receive a piece of scientific information. Shall I be able to reproduce or to replicate, use my own data or use the information of the authors in a way that I could arrive at the similar conclusions or at the same level of conclusions? That's the core idea. So when you say the same conclusions or similar conclusions, probably you are going to dance between reproducibility and replicability. But the core idea is that I understand and reproduce at some level a published paper. So for me, this is the core question that we are dealing here today in this webinar. Again, reproducibility refers to independent researchers arrive at the same results using their own data and methods, while replicability refers to a different team arrive at the same results using the original author's artifacts. So it's slight different between each other. So now I'm going to present some my own problems and to exemplify this situation. So first of all, reproducibility of chaos simulation. So probably some of you have already heard about chaos theory or dynamic chaos. So chaos is a name that people found in the late 70s and 80s, that when you were going to simulate, and in the late 80s, even experimentally as well, we could find some deterministic simulation, but that behave quite randomly. And although there are lots of research about that, there's still open questions and a lot of applications about that. So in this paper, we investigate the reproducibility of the chaos simulation of the Jack secret proposed by the author Sprott. So what is a Jack dynamics? The Jack dynamics is a nonlinear function J called Jack. It describes a third-order derivative of x, which corresponds to the first derivative of acceleration in mechanical systems. This system describes the following. So I have here a third of derivative, and there is a function J that relates my three variable states here. x second derivative, x first derivative, and x no derivative here. So this is the electronic circuit that myself and my PhD students and all the collaborators we reproduce. So this electronic circuit here, it's represented by this schematic here. And with this electronic, I just put this in a voltage source, and this is going to behave in a very different dynamic behavior. The problem is that when I'm going to simulate, I try to use a unique software called LT-SPICE. This is a software designed to reproduce, to understand electronic circuits, but I use the same version in 4 different computers. All these computers are based on Windows, but with different core systems. All of them Intel, but slight different processors. So what happens that these are my 4 simulations, and you're going to see here they are almost the same. You cannot perhaps spot the difference with only eyes here. And my question is that which computer is correct or more correct than each other? So this is the question that I try to answer. And before that, I'd like to say something about when I say what is correct, what is precision. So usually in engineering, we have this trade-off between accuracy and precision. So in this figure A, I have my aim of an instrument or a computer simulation. This is something that it's really, really important. Many people don't think that a computer is an instrument, is an equipment, a machine. But it's a machine as any other. So as a voltage measure or a temperature device that I'd like to measure the temperature, any of these instruments, they have some structure that try to imitate, try to measure reality. And or in a computer, when I'm going to deal with simulations, I'm trying to represent the behavior of differential equations or computer simulations that try to imitate reality. In both scenarios, I'd like to try to reach my perfect solution. In figure A here, I try 3 times, and both times they don't get the good results. But even worse, they present different outcomes. So in this case, I say low accuracy and low precision. Let me emphasize here that this is the way that people from engineering, from measurement background, they try to investigate results from machines, from device. I usually incorporate that background in my computer simulation because I'd like to deal with computer as any other machine. In figure B, on the other hand, I still don't get my best results, but all of my simulations, they are very close to each other. So in this case, I say that my simulations, they present low accuracy, but high precision. In figure C, all of my simulations, they very close with my results. They have better accuracy, but they are not close to each other. So they have low precision. And finally, the best of the worlds, figure D, I have high accuracy and high precision. So when I try to use this idea with my simulation, I try to imitate those results experimentally. So when I try to do that, this is the comparison with my simulation with the 4 computers and with a real data I produce. So computer 4 is chosen as a reference since it shows slightly better performance than other computers. So this is the square error, the sum of square error, normalize it, just to try to see which computer. So although they are not so different, you see here, computer 2 presents quite a worse, a bigger error than others. So, okay, so when I try to do that, I also try to give more details about everything about my data. So I use OSF platform to try to give all the information about my code. So this is one of nice platforms that you could give supplementary material for your research. So in this case, I put title of project, project author, a weak description, all files related to the project, code files to use, illustrative example, how humid simulations of my software, and so on and so forth. So this is a way to try to support the authors in a way to reproduce the results. And why is important to reproduce the code? This is a very simple simulation that I'd like to emphasize the difficulties that I have here with simulation. So this is an interactive simulation with this map. So how I simulate this map? I start with xk with an initial condition. For example, in this case, I put here something around 0.9. So 0.9, this is my first value. And the second value is 4 times 0.9 times 1 minus 0.9. This second function here is the same as the first one. Just I open the brackets. I use associative code. But using MATLAB in Windows, when I'm going to implicate these two results, both results present completely different outcomes after a couple of iterates. Although they are mathematical equivalent, the results in one of them, they reach a fixed point. What it means? It's stuck in this value around 0.75, and the other one behaves as chaotic behavior. It's randomly. So this is the importance of code. When you see any computer, any equation in a published paper, if you don't have access to code, it's really difficult because there is a lack of reproducibility in a computer. Why? Because finite precision in a computer does not have basic properties as you have in real systems, in real number representation. And those basic properties does not guarantee very basic associative and distributive base. Technically, we say that a finite precision in a computer is not a field, as you say in mathematics. Just to say that a nice way to try to deal with problems is with reproducibility is called Ocean. This is something that I myself should explore a bit more, but the idea is quite good because the idea is that we are going to create a capsule, and this capsule, it has not only the same version of the software, but also hardware. So this is one of the best ways that I could think in a long-term journey to reproduce simulations in a long-term future. Another example that I like is the idea of cryptography. Cryptography is also very present in our daily life because you usually use passwords all the time to access our mobile phones, to access our computer, to get money from bank, to make bank transfers all the time. So what's the idea of cryptography? The idea is cryptography that Alice is going to send a message to Bob, but using an unsecure channel. And this unsecure channel, I have here some adversary. This adversary is going to try to cope or try to have access for the information that Alice is going to change. So this is a very classic way to describe cryptography. And so Alice is going to have the plain text source, and before to send the information, Alice is going to encrypt the information, and the information that's going to be sent is encrypted. When Bob received this information, he has to decrypt this information with a password, with a key. An example about that, so a key E maps each letter to win one is 3 positions to its right. So for example, this is a very basic, usually girls and boys in primary school, they used to send messages encrypt for each other. So I'm going to change A to D, B to E, and so on and so forth. So with that, a message. This cipher is certainly not secure, and is going to be T is going to be by letter W, U is going to be X, and so on and so forth. So this is just a way to use this information. But in reality, many aspects is not going to be that one. You can use, for example, very useful, the Werner cipher. The Werner cipher is a binary message that I'm going to use XOR to represent that. So I have a message here in binary. So it's a long sequence of bits, M1 to MT, is operated on binary key string, K1 to KT, on the same length, to reproduce a cipher test C1 to CT. So M1 is the message that I'd like to encrypt. Key1, key is my cipher, and C is my encrypted message. And just some of you probably some of you could not have a background on Boolean algebra or even engineering. So this is how can XOR cipher works. XOR is a Boolean algebra that as AND or it produces one only when its inputs are different. So if 0, 0, it's going to be 0, 1, 1 is going to be 0, but when you have 0 and 1, or 0 or 1 and 0, it's going to be 1. But it has nice properties because A XOR 0 is A XOR A is 0, A XOR B is equal to B XOR A, and more important for cryptography, when you apply B XOR A, and again XOR A, you have B. This is wonderful because, so this is why cryptography works. So when you have here B XOR A, you produce encrypted. But if Alice has the password and Bob has password A, you are going to reproduce B. So this I'm going to put here in just an example. So when you have a string of bits, you reproduce XOR, and you are going to have a different bit. And this could be useful for decryption as well. So reproduce XOR again, we are going to produce the same results as here. But with an image, it's going to be much easier to try because image usually very easy way to try to reproduce this information. So usually you are going to send images in the internet and you are going to try to reproduce this information. So an image in a grayscale, you can read with any code, and usually you have a matrix of integers. And a pixel encryption could be seen as well in this way. So each pixel has an integer number, and this integer number could be described as binary. I'm going to apply XOR, and I'm going to have a completely different color here. So the beginning is 30. When I apply my password, it's going to be 197. And finally, I have completely different pixels here. So this is used to do what? To encrypt image. So I have an image here. I apply XOR. So everything that I said from my previous couple of slides is to show that I'd like to send an image. Before to send an image, I encrypt. So it's meaningless. I cannot see anything here with any meaning using XOR. And finally, when I have the password, I can reproduce my words. So the problem is that with my own research, people in many papers, what happens is that they use CALs to reproduce that. And what I discover in one of my papers is that when I try to reproduce many papers, I use a different device. So, but this is real life. Many people, they are going to try to test the encryption schemes using a unique computer. So what happens that the computer presents a slight difference between each other. So when I try to apply different schemes, different encryption schemes, I use the same approach. I use the plain image and the encrypted image device 1, and I try to decrypt this image in a device 2, and I was not able to do it. So this is a crisis in this area of cryptography, because in many situations it was not possible. So over the past 3 or 5 years, I'm trying to solve this problem, and the line 2 here is one of preliminary results, and I was able to reproduce the results in a different computer. And in 2021, using a stronger way to represent numbers based on this theory of Galois field, I was able to reproduce, to decrypt correctly, even in a different computer. So this is, although this is a crisis, but it also represents an opportunity for scientific research. So from here, with these 2 examples, what I'd like to emphasize is that sometimes it's really hard to reproduce, even if you have very decent details on your published paper. If you don't understand the phenomena very correctly, for example, in this case, in the cryptography, some people, they don't understand that computers can represent numbers in a different way. In such a way, it's not going to be possible to reproduce my results. Yeah. So just a couple of more slides that I'd like to present here, perhaps more to present as questions than my own clarity about that. So reproducibility versus patent, so or intellectual property. So this is really hard when you're going to think very carefully about that. So hide the secret, avoiding independent test. This is usually when you're going to try to keep your own. But if you are going to not to be able to other people to criticize your own research, you are going to keep the myth. So the practice of university patent involves an academic attitude, thus, by inciting an attitude towards knowledge that's not consistent with the proper attitudes and goals of university, university hurts university's integrity. So this is a very nice paper about Cristina de Campos, the idea of patents versus the idea of university, published in 2015. So this is a nice paper that discusses the tension and the trade-off between intellectual property and the idea of university. So this is why our discussion here is so important, because at the end of the day, what we are discussing, it's the core idea of university. If you understand correctly what is science, what's reproducibility, and with patent, we can, of course, arrive, okay, let's achieve a consensus that is still important to have patent. But we have to clarify the limits of our understanding about university. And again, sometimes I think that a patent-free university could have some space in our society, or at least some universities or some departments should try to be patent-free, as you have gluten-free and other stuff in your market. So conclusion, open science, in fact, emphasizes in what science is about. Sometimes, to be honest, when I was preparing this talk, I realized that do we need this adjective behind science to say open science? Or when you're trying to describe what is about open science, we are in fact describe correctly the meaning of science. So for me, it's quite interesting. Sometimes it's important to emphasize some aspects of science, but on the other hand, it seems that, okay, so there is an open science and there is something that is science, but it's not open. That's for me another question that I have no clear answer for that. And reproducibility, for me, it's a way to keep science out of methodology. So for me, it's an important aspect about that. So that's it for me. I'd like to thank so much for keep attention and to give the opportunity to discuss this. And I'll be happy to try to make any comments, to try to answer. And of course, I'm here as any and not so different from each of you to try to clarify my own ideas about science and about reproducibility. So thank you very much. And now I'd like to give the word again to Pablo.